Okay, so I'm going to start by just setting up the notation of the talk. So the first thing is that we're going to consider throughout this talk R to n endowed with the standard symplectic form. So with the symplectic form omega 0 equal dx1 which dy1 plus dxn which dyn, where x1, y1, xn, yn are the coordinates in R to n. Okay. And for this talk, all subsets of R to n are also equipped with the restriction of this form to the corresponding subset. So are equipped, endowed with the restriction of omega 0. Okay. So now let me set up the notation. And I'm going to define the three main objects that I want to consider in this talk. The first one is the 2n ball of radius r. So sometimes this is open, sometimes this is closed. For me, this is going to be open. So this is denotes the open 2n ball in R to n. So that's the first of radius r, i.e. this is the following set. Such that the sum of the squares of the coordinates is less than r squared. Okay? So this is the 2n ball of radius r, the open one. Now, for r positive, the cylinder of radius r, which is again another open subset of R to n. This is the set of points such that x1 squared plus y1 squared is less than r squared. Okay? And finally, I'm going to give an example, which is the ellipsoid. And both 1 and 2 can be considered examples of ellipsoids. So the ellipsoid is defined for parameters a1 up to an, where I allow plus infinity. And I allow plus infinity, you're going to see, so I can get the cylinder as a particular example of the ellipsoid. So take these values. I define the ellipsoid a1 e of a1 an to be again the set of points in R to n. Such that the sum of the squares divided by these parameters is less than 1. So this is the ellipsoid with parameters a1 up to an. And you can see very quickly that if you allow plus infinity here, you can get the cylinder by just taking all the parameters a2 up to an to be plus infinity, and just thinking that if you divide a number by plus infinity, you get 0. So 1 and 2 are examples of ellipsoids. So this is ellipsoids. Okay, so these are the three main open subsets that I'm going to consider in this talk. And now I want to discuss symplectic embeddings. which are going to involve these three sets. So in this talk, just to this arrow like this is going to mean a symplectic embedding so if I don't say anything, that means symplectic embedding, not just embedding. Okay. So here is a striking result that was proved by Gromov in 1985. So this is the Gromov non-squeezing theorem that says that the ball, which I just defined here, this open ball, can be embedded into the cylinder of radius r. So you have a symplectic embedding of the ball into the cylinder, maybe I should say, exist if and only if the radius of the ball is at most the radius of the cylinder. So the classical picture that people draw is something like you have r here and you have the cylinder of radius r here. This tells you, the theorem that Gromov proved tells you that you cannot squeeze this ball here if the radius of the cylinder is smaller than this radius. So you cannot do this. So this is not possible now if r is greater than r. So this is what Gromov proved. So, and you can of course see why this is called non-squeezing, because you cannot squeeze the ball. So ball cannot be squeezed if it's bigger into cylinder. Okay. So Gromov proved this theorem by studying properties of moduli spaces of holomorphic curves. And since Gromov gave this proof, there's been a number of other proofs. So, for instance, Hofer and Zender gave a proof using Hamiltonian dynamics and original calculus, and using those ideas that they introduced in that proof, they were able to get very far and construct a number of symplectic invariants. So let me just make a note on this theorem. A quick note is that Gromov proved it using, or maybe by studying properties of moduli spaces of pseudo-holomorphic curves. And then now more proofs are known. Notably by Hofer and Zender. Using Hamiltonian dynamics. And then there are other proofs by Viterbo using generating functions. And then there are several approaches that mix everything. Okay? So that's the first note I wanted to make. And also I want to make another note, which is that Ekeland and Hofer pointed out that you can also prove the non-squeezing theorem. You can also deduce the non-squeezing theorem from a previous result by Eliasberg and Gromov, which is called the Eliasberg-Gromov rigidity theorem. So also Ekeland and Hofer pointed out that the previously known Eliasberg-Gromov rigidity theorem can be deduced from Gromov's non-squeezing. Okay. So the Eliasberg-Gromov rigidity theorem says that the group of symplectomorphisms is C0 closed or in the compact open topology inside of the group of diffeomorphisms. So that was a very important result that was proven earlier. Which one? This deduction. Okay. Does it go the other direction?
No, so using the non-squeezing theorem, you get this.
Okay. So now I want to come to the main question of this talk, question 1, which was posed by Hofer in 1989. The question is there a positive radius? Is there R positive? Let me call it capital R, such that the cylinder, the 2n-dimensional cylinder of radius 1, so just I can write this as the ball cross R to the 2n minus 1. So this is the cylinder we just saw. Okay. This cylinder, can it be such that can be symplectically embedded into B, this product B to the 2n minus 1 R cross R2. Okay? So this is another squeezing, non-squeezing type question. Can you embed the cylinder of radius 1 into some product of this form? So notice that here you have many copies of R, and here you only have 2. So this is much smaller, if you like. So let me start by making some notes on this question of what is known so far. Maybe I can continue here. So the first note is that if there is such an embedding, then the Ekeland-Hofer theory of capacities already tells you that the radius has to be at least square root of 2. So this is by the second Ekeland-Hofer capacity. So I just want to make this remark here, but then I will define capacities just in a second. But for now, I'm just going to make this remark. The Ekeland-Hofer theory of capacities implies that if such R exists, if such R exists. We don't know if it does, but if it does, then R has to be at least square root of 2. Okay, so that's the first. This is observation. It still, of course, doesn't tell us whether it exists or not. Now, around 2007, Larry Guth proved the following. Proved, or it follows from his work, proved that there exist R positive such that the following is true, such that you have an embedding B2 1 times B2 to the n minus 1 S, which is symplectic, into B4 R cross R to the to n minus 2. So Larry Guth proved this result for all S positive. So you can find a radius R such that you can always embed for a fixed radius, for a fixed S, you can always embed it here. So let me call this embedding star. And now you can make the following observation as well. Richard Hint and Eli Kerman. This was around 2009. Refine Guth's method and showed and proved that if an embedding like this exists, then the radius has to be at least square root of 3. And they prove that it exists if the radius is at least square root of 3. And they prove that it doesn't exist if the radius is less than square root of 3. So if an embedding, so let me write this, refine Guth's method and prove that if this embedding exists, then R has to be at least square root of 3. And constructed such examples. Maybe that's what I constructed them. So I think that's what I mean. So the only case that is left is R equals square root of 3. Okay?
So was Guth's proof by explicit?
Yes. So Guth's proof was by explicitly displaying an embedding. Yeah. And then this they refined Guth's proof and got this optimal bound. So they also proved that if R is less than square root of 3, you cannot have such an embedding. And so the only case that was not covered in that paper is the case of R equals square root of 3. And I answered that case with my collaborator San Vu Ngoc. By the way, everything I'm saying is joined with San Vu Ngoc. So San and I proved that, this was last year, that if R is equal to square root of 3, then such embedding also exists. Okay, so now I want to make I want to make a final remark on this. So 5, the existence of this embedding, the existence of this embedding implies that there is some R positive, there is some radius R positive for which we can answer the, so to speak, bounded version of Hofer's question. So for which b to 1 times b to the 2 n minus 1 s embeds onto b to n minus 1 r cross r2. So the only difference here with the question is that instead of r to the 2 n minus 1, I have a ball here. So for every fixed s, you can do this. And the question is, can we work our way up to be able to replace this bounded component here by r?
I guess the point, just to make sure.
Yeah.
The R is independent of S.
Yes. Yes, exactly. Yeah, for which, very good. For large S. Yeah. So hence these answers question, the bounded version of question 1. Okay, so this was what was known until around 2009, and I want to now state the theorem that San and I proved last year. So the theorem says the following: the answer to question 1 is yes. The answer to question 1 is yes. More precisely, we have an embedding of the cylinder of radius 1 into the 2n minus 1 ball of radius r cross r2 when the radius is at least 2n minus 1, square root of 2n minus 1 plus 2n minus 2 minus 2. Okay, and of course I didn't say if and only if because we don't know. In fact, we do know that this is not sharp because if n is equal 3, we have another result that gives us a better number than this. So for n equals 3, this gives you 2, and we know that the sharp number for that case is square root of 3. So this is not a sharp.
So you think it's square root of 3 or is it sharp?
I don't know. Yeah. I don't know. Yeah.
So is it easy to get from star to this embedding?
You have to repeat sort of the same argument several times. So in the first time, you get here r to the 2n minus 2. Then you apply the same argument with care. It has to be done with care because the parameters need to be worked with care here. But you can at each step decrease a copy of R until you get to R2. But all of this depends on concrete estimates, so it has to be, yeah. Yeah. Huh? Yeah. So for everything I'm saying, I assume that n is at least 3. Yeah. Yeah, if n is equal to 2, if n is equal to 2, most things should also hold. The ones that make sense should also be true. Huh? Here? Yeah. So let me say we assume n at least 3. For n equal to, most things can be answered immediately as well. Okay, so let me just make some remarks in this. So the first one is that this result is not sharp, and we don't know how to approach it, because the embedding constructions that lead to this theorem, we don't know how to refine them anymore. So so that's the first note on the theorem. Is that the theorem is not sharp, while the bounded version was sharp. We knew it for all values. For instance, if n is equal to 3, then if n is equal to 3, let me just, instead of writing the details, it's known that R equals square root of 3 is the sharp. So after square root of 3, you have embeddings, and for less than square root of 3, you don't have. So this was proved by San and I also last year, and this both this and the previous observation, they both rely on the same on the application of the same theorem, which I'm going to state in a minute. So of course it would be very interesting to improve this bound. I don't know how to do it, but it would be very interesting to do that. So let me now connect with the title of my talk, which is symplectic capacities. Let me set some notation. So for fixed n, simple to n, this is going to be the category of 2n manifolds of 2n dimensional symplectic manifolds with symplectic embeddings as morphisms. With symplectic embeddings as morphisms. So this is very large. And inside of this category, you have, for instance, the ellipsoids. So all the ellipsoids, which are subsets of R2n, they are in this category. So let me call that category L2n. This is going to be the category of 2n dimensional ellipsoids of 2n symplectic ellipsoids. And the embeddings are going to be those that are induced by global symplectomorphisms of R2n. And So in between these two categories, you can have many examples of categories, and I'm going to be interested in symplectic categories. So let me say what this means. So asymplectic category is going to be a subcategory of this category that satisfies the following property. So it's a subcategory of the category of all symplectic manifolds with symplectic embeddings as morphisms. It's a subcategory. Let's see. Let me call it C of this, such that the following is true. If the symplectic manifold M omega is in the category, then I can rescale the symplectic form, and the result is also inside of the category. So this is also here for all lambda positive. Okay? And now I come to the definition of capacities, which is due to Ekeland and Hofer, and also to Hofer in the case of higher dimensional capacities. So this is around 1989, right? So take C as symplectic category. So that's a definition. Let's see the asymplectic category. And to avoid trivialities, we always assume that this category contains at least the ellipsoids. Okay? So let's see the asymplectic category containing the two n-dimensional ellipsoids. And remember that the two n-dimensional ellipsoids, because you allow the parameters to be plus infinity as well, it contains as particular examples the cylinders and the balls. Okay? So now fix an integer d between 1 and n. Then a symplectic d-capacity, is the following. It's going to be a map that assigns to a symplectic manifold a number between 0 and plus infinity. So a symplectic d-capacity is a functor C, call it little c, from the category, the symplectic category, into 0 plus infinity, where this gives the morphisms. So if you like, this just means that this is a monotone map. So if you have a symplectic embedding from M into M prime, then the capacity of M is at most the capacity of M prime. So in particular, this functoriality already tells you that capacities are symplectic invariants. So this is a functor such that the following properties hold. The first one does not involve the parameter dz, which I just fixed. So the first one is conformality normality. This is for all lambda positive, the capacity of m lambda omega. So if you multiply the symplectic form by a number, then the capacity gets multiplied by the number. And the second one is the one that involves the parameter d, is the d non-triviality. Non-triviality. So the d non-triviality says that the capacity of the ball of radius 1 has to be positive. Okay? Sometimes you require that this is 1 or pi, but let's just require that it's positive. And two things. The capacity of this product, b2d1 times r to the 2n minus d. This is less than plus infinity. And the capacity of 2b minus 1, 1 times r to the 2n minus d plus 1 is equal to plus infinity. Okay. So you want the capacity of this product to be finite. You want to be measuring area in this dimension, and the capacity of this to be infinite. So notice that what the difference between this and this is that here I have one copy of r more, and here I have one copy of r less. So this is what this means to be the non-triviality. And the first remark I wanted to make is that, as I just said, by the functoriality you have that these capacities give you symplectic invariance. Okay? And now you can ask the question, well, we have a definition. Can we find, we have a definition that we know is going to give us symplectic invariance, which are very fine. Can we actually construct capacities? So the first capacity was constructed by Gromov in 1985 before the general definition was made. And it's called the Gromov radius. So let me make a remark on this. So remarks. The first symplectic 1 capacity normally symplectic 1 capacities, you call them symplectic capacities. The first symplectic 1 capacity was constructed by Gromov. Was constructed by Gromov. Also in 1985. And it is called the Gromov radius and is defined as follows. The capacity of a symplectic manifold is going to be the radius of the largest ball that you can embed into the manifold symplectically. So this is the supremum of all the R positive such that there exists a symplectic embedding of the 2m ball of radius R into the manifold. Okay? So that's the first example of a symplectic 1 capacity. And if you haven't seen this before, you can try to start checking the properties and see that it all seems to go very fast until you get here when you put d equals 1. And then you have to check that the capacity of the cylinder is finite. And that's precisely the Gromov non-squeezing theorem. So the fact that the Gromov radius is a 1 capacity is equivalent to the squeezing theorem. So this is a 1 capacity by the non-squeezing theorem. Okay? now the next observation I want to make is that the symplectic volume gives you an example of an N capacity immediately. So this is one. So second, the volume, or some rescaling of the volume, C, maybe call it B, from C. B of the manifold M omega, just the integral of omega n over n factorial to the 1 to the n. This is an N capacity, a symplectic N capacity. Okay? So we have left to decide what happens in between 1 capacities and N capacities. And these capacities were called intermediate capacities by Hofer, and that's the title of my talk. So let me state this as a question. Question 2. Do intermediate capacities, do symplectic d-capacities exist if d is between 1 and n on some symplectic subcategory, on some symplectic category C of the category of 2n manifolds with symplectic embeddings as morphisms. Okay? So this is the question, and now I can connect with the previous discussion on embeddings and say that the work of Guth implies that you cannot have, implies that there are no intermediate capacities provided that you have some exhaustion property. Let me explain this, why this is true. So note, it follows from the work of Guth. From the work of Guth on embeddings, which I mentioned in the first part of the talk. It follows from the work of whom I mentioned earlier. That intermediate capacities do not exist provided the following property is satisfied. Maybe let me just say here. So these are called intermediate. So I don't have to write every time the entire text. Work of Guth mentioned earlier that intermediate capacities which also satisfy the following property, which also satisfy exhaustion. Do not exist. So by this we mean the value of the capacity, on open subsets can be obtained as the supremum of the value of the capacity on bounded subsets. The value of the capacity on open subsets is the supremum of the value of the capacity on bounded subsets and this can be refined a little more, and Guth writes some limits that are implied by this in his paper. So that cannot exist. Let's see. Yeah. Okay. So the question is, what if you don't satisfy this property? And this is the second result that San and I proved, San Vu Ngoc and I proved. And the analogy between the bounded version of the first question of Hofer and this one is the same as the analogy between the first theorem I stated that San and I proved and the theorem I'm going to state right now. So theorem 2. The answer to question 2 is no in general. The answer to question 2 is no. More precisely, you cannot construct intermediate capacities on any symplectic category. More precisely, intermediate capacities do not exist on any symplectic category. And of course, I'm always assuming that at least my category contains the ellipsoids, otherwise the d non-triviality cannot be stated, right? Okay. So therefore, in view of this theorem, the conclusion is that you only have capacities in the case of d equal 1 and d equal n. So maybe. Where did I say bounded?
What is bounded?
Ah, yeah. Yeah. Thank you.
How bounded as compact closure?
Yeah. Yeah. Thank you. So this theorem, this second theorem, can be deduced from the first theorem on embeddings. So you assume that there is such a capacity, and you construct an embedding of this into this, and therefore you get a contradiction. So the proof of this theorem, given the first theorem that I stated at the beginning of the talk on symplectic embeddings, leads you to an embedding from this into this, therefore a contradiction. So that I'm going to skip that proof, and I'm going to give an idea of the proof of theorem 1.
Actually, it meant that embedding from the lower to the upper.
Oh, yes. Very good. From this one to this one. Yeah, thank you. Yeah. So the idea of the proof of theorem 1 is as follows. So the first step is to prove that certain constructions that Guth and Hin and Kerman did can be also implemented when you vary the parameter smoothly. So So let me maybe say that this is proof a smooth family version, a smooth family version of Guth, Hin, and Kerman results mentioned earlier. So these constructions fix the S, and for that fix S, you have an embedding. And the way we are going to prove this theorem is by saying that you can implement those constructions when the S varies smoothly. Okay, there are more parameters, but roughly speaking, when the S varies smoothly. And then the second step is going to be to pass to the limit. And this pass to the limit, so this pass to the limit is what I want to explain next. But maybe let me say in this first step, roughly speaking, the family that we're considering. So prove a smooth family version. So I think I erased it, but I'm sure you see what I mean. We had this. I said that the second theorem I stated, sorry, the first theorem I stated was an unbounded version of the result that I had mentioned before of Guth. You had these two balls, and you could embed them for any radius of the second ball into a product. And we said that we want to pass to the unbounded case, right? So the first step amounts, roughly speaking, to checking that that construction can be made smoothly with respect to the parameter S that is in the domain. And there are many more parameters involved, and but that's roughly the idea. And the second idea, sorry, the second step is the one I want to mention now. So we want to apply the following pass to the limit theorem. So let me state this theorem. You see what I mean by step one, right? I'm sure you see what I mean. Okay. So let me state the theorem. So suppose that we have the following situation: take an omega to be a symplectic manifold, and take omega t containing n be simply connected, open subsets simply connected open subsets, and assume that they are nested in the following sense. Simply connected open subsets such that omega t, the boundary of omega t is contained on the boundary of wt is contained in the closure of ws is contained in wt, and this is nested in this direction, so they become smaller. And now take a family phi t of symplectic embeddings, and I'm going to assume that this family is smooth. So this is smooth family of symplectic embeddings such that with
So smooth means here if I take a point in WT0, then isn't the point lies on nearby values also there.
yes,
Then it was together with the T, it's smooth.
yes, that's roughly speaking what it means. Yes, yeah, yeah. We define explicitly in the paper, and that's essentially the idea. Yeah. So suppose that you have such family of smooth symplectic embeddings, and we need one more property on this family. Smooth family of symplectic embeddings such that the following is true. This is a relative compactness property such that for all ST, the union of these images, phi v WV, is relatively compact in M. Then the following is true. Then there exists a symplectic embedding from the union of the WTs into M. Okay, so this is the theorem. You have a smooth family of symplectic embeddings that satisfies some relative compactness property. This property is here because the proof is done using Hamiltonian flows to modify symplectomorphisms, and for the flows to exist, we need some compactness, and this is where this assumption comes in. So let me draw a picture to illustrate this theorem, because the theorem doesn't tell you that if you have a smooth family of symplectic embeddings, then you have a limit. It tells you that if you have a family of symplectic embeddings like this, you can modify the family so that you can construct a limit in this sense of constructing an embedding from the union of all these sets. But this limit embedding is not related in principle to any of the embeddings in the family. So you can think of this is the picture. You can keep in mind you have the family omega t here of sets omega t, and now you have embeddings. So these are, and the images of these embeddings come to things like that. Okay? And you want to construct an embedding from the union of all these sets. Okay? So of course, there is no reasonable way to talk about a limit here. So what you have to do, the proof goes through modifying these embeddings here suitably using Hamiltonian flows to construct this one. So this is the main tool that we explain in the paper, and using that tool and the fact that you have a and the fact that you have the bounded version of the result of Guth and Hinn and Kerman smoothly, you can use this theorem to pass to the limit. And so using this same tool, you can also get the proof of the endpoint cases which I mentioned earlier. I mentioned that there were some results that you knew if r is greater than square root of 3 and if r is less than square root of 3. And we didn't know the case r equals square root of 3. And using this same method, you can answer that. So there are another couple of questions of Hinn and Kerman to which you can apply these to answer them. So what I discussed today is in 2 papers. The first one is in the archive. It's called Hamiltonian dynamics and symplectic capacities, and that paper has been split into 2 papers. The one paper that contains the answer to both of the Hofer's questions, and another paper that contains the answer to a question of Hin and Kerman about an endpoint case. So, yeah, thank you.
Thank you very much. Question?
Yeah.
So this thing about the square root of 3, they're indeed existing kind of embedding.
Yeah.
Is there any kind of like general expectation that for embedding problems on the borderline there will be an embedding?
So my expectation is yes because of this. Because using this result, once you have existence in an interval 0a, you also get the existence at 0. So I think the answer, I don't know if in every case, but certainly if I saw a result that is proven for all values by 1, but one value, and I know that in one direction you have existence, I would try to get the existence also in the endpoint using this. You need some conditions here that needs to be satisfied, but yeah. So I don't know in general, but I would try to prove yes if I could apply this theorem.